Hi, this is Jean from Université de Montréal. This video will discuss image generation and signal adjustment. This is part of a video series on fundamentals of ultrasonography. Please visit our YouTube channel Sonovault for additional educational content. At the end of this video, you will be able to understand the physical properties of ultrasounds, understand the interactions of ultrasounds with tissues, and understand image generation and optimization of resolution. We'll first start talking about the physics behind ultrasound, as they are quite relevant to understand how image is generated and how the ultrasound can be optimized. Sound is a type of wave that carries energy. It is a mechanical wave created by the vibration of a transmission medium after transfer of energy. As such, it cannot travel through a vacuum. Contrary to popular belief in ultrasonography, air does not block ultrasound waves. Its unique properties, mainly related to velocity, make its interface with tissues strongly reflective to ultrasound. The energy left cannot travel far in the next solid and create images. Ultrasounds in solids is transmitted as a longitudinal wave or compression wave and transverse waves. Longitudinal waves are alternating pressure deviations from equilibrium with areas of compression and rarefactions. Transverse waves are shear stress perpendicular to the direction of propagation. For the purpose of this talk, we will focus mostly on longitudinal waves, which are most important for our applications. Tissue at equilibrium has no areas of compression or rarefaction. The energy of an ultrasound waves create those areas. Compression areas are high energy, while rarefaction areas are low energy. Sound waves are often simplified to a sinusoidal plane wave, characterized by the following properties: frequency, amplitude, speed of sound, and direction. The frequency is the time between the two compressions and rarefactions. Its inverse is the famous wavelength, which is the critical property that influences interactions with body tissues and image production. Amplitude represents the sound pressure or intensity and depends on the power that the machine transmits to tissues. The speed of sound that we are typically thinking about is in our ambient air. This remains true in body tissues, although it is faster and for the most part can be considered constant despite the slight variations in density. It is around 1540 meters per second. Sound velocity varies significantly depending on the transmission medium. This is related to a combination of density and stiffness. Air is low density and highly compressible, while bone is dense and stiff. You can see on the schematic that air is a low velocity medium for ultrasounds. Most tissues within the body are of more or less equal velocity. Bone is the exception, as it has high velocity. One important point is that the frequency of the ultrasound waves does not change while it passes from one medium to the other. The result, based on the equation seen here, is that the wavelength increases with increasing velocity. This has an impact when interacting with tissues. Ultrasound waves have energy dispersion while traveling through tissues, and thus loss of intensity of returning signal. Attenuation is the loss of intensity with increasing distance traveled due to scattering caused by interactions with tissues. This is not entirely lost, as it creates a signal interpretable by the ultrasound. Absorption is the transfer of energy to tissues that result in heating. Each tissue has unique attenuation coefficients for energy loss. These two processes explain the limits to depth generation with ultrasound. The combined effects of scattering and absorption result in exponential attenuation of ultrasound intensity with distance traveled as a function of increasing frequency. When expressed in decibels, a logarithmic measure of intensity, attenuation linearly increases with ultrasound frequency. Hence, a 10 MHz transducer will have 5 times the attenuation per unit of distance compared to a 2 MHz transducer. Knowing this, there is a potential to compensate for signal based on depth. This is done using the time gain compensation. Simply, it takes longer for a deeper structure to have an ultrasound reflect on it. We can thus amplify the signal in order to display it with the same intensity as tissues close to the transducer. It is important to understand that we are not generating more signal, we're just amplifying whatever comes back. Reflection governs most of what we perform in ultrasound. When an ultrasound hits a structure, part of the energy is absorbed, but a large part is reflected back. This can be done in an organized manner, also called specular reflection, or a disorganized manner, also called non-specular reflection. Specular reflection happens when the ultrasound waves are larger than the elements they are interacting with. At low frequencies, 1 to 5 MHz, wavelengths are relatively large, and tissue boundaries appear smooth or specular, mirror-like. For the most part, this happens at interfaces between two tissues. Non-specular reflection arises from objects and interfaces within a tissue that are about the size of the ultrasound wavelength or smaller. At higher frequencies, wavelengths are smaller and boundaries become less smooth, causing echo reflections in many directions. A non-specular reflector represents a boundary that represents many different angles to the ultrasound beam, and returning echoes of significantly less intensity. Of course, more than frequency related, this is a property of the tissue being imaged. Refraction is a different physical element and related mostly to artifact generation. The key message here is that all image generation of real, properly displayed tissues within the body are resolved using a subtype of reflection. These coexist in most images you see. Tissue delimitation, as in distinguishing two different structures, is usually clear because it represents a specular reflection. This process happens because of differences in acoustic impedance between the tissues. Basically, acoustic impedance is a measure of tissue stiffness and flexibility and is the product of density and speed of sound. Acoustic impedance is intrinsic to tissue. Air has low impedance and bone has high impedance. Between tissues, it is the relative difference in acoustic impedance that determines the degree of reflection. A high relative difference leads to a high reflection. Notice how this is unrelated to which one of the input or output tissue has the highest velocity, such as the bone to fat versus fluid to bone. This is strictly a relative difference. Of course, bone has such high impedance that very little signal makes it through for the phenomenon showed above to be ever demonstrated clinically. This is an excellent example of acoustic impedance. In this parietal axis view, there is myocardium, pericardial fusion, pericardium, and pleural fusion. Clearly, the pericardium is a strong reflector, which may relate to its more fibrous nature and acoustic impedance compared to fluid. There are two terms often used, diffuse reflection and scattering. These are essentially synonyms. Scattering is most often used in the context of non-specular reflection within tissues. Diffuse reflection is more commonly used for non-specular reflection at an interface between two different tissues. Scattering governs intratissular echogenicity and resolution, and constitutes most of the non-specular reflection seen in clinical applications. Many organs can be identified by a defined signature, caused by intrinsic structures that produced variations in the returning scatter intensity. Scatter amplitude differences from one tissue region to another results in corresponding brightness changes on the ultrasound display. In general, the echo signal amplitude from a tissue or material depends on the number of scatterers per unit volume, the acoustic impedance differences at interfaces, the size of the scatterers, and the ultrasound frequency. Higher scatter amplitude tissues are called hyperechoic, and lower scatter amplitude tissues are called hypoechoic, relative to the average. The amount of ultrasound energy imparted to the medium is dependent on the pressure amplitude variations generated by the degree of transducer expansion and contraction. This is controlled by the transmit gain applied to a transducer. Power is the amount of energy per unit time introduced to the medium. Intensity is the concentration of the power per unit area in the ultrasound beam. Power does not equal gain. Gain artificially amplifies the returning signal, but is not helping generate additional signal. Increasing power leads to more reflective signal being generated. These have two different settings on the machine. Refraction is an interesting phenomenon that we will cover more in the artifact generation section. As we described, air does transmit ultrasound. However, as you've seen, this has very high relative acoustic impedance with most tissues, and thus high reflection. Very little signal is thus available for deeper tissue interactions. Image generation can be understood using all those principles, and we will go over them now. First off, we have to talk about a transducer. A transducer is a generator of ultrasound waves using piezoelectric crystals that serve as emitter and receiver. We will not go into massive detail on how a transducer works, because it is not as useful clinically in most instances. We will not go in all the different mechanical structures that play into the ultrasound transducer. The transducer sends small packets of wavelengths organized in cycles. Multiple cycles are sent and are called spatial pulses. The spatial pulse is a defining unit of energy that will interact with tissues and produce specular or non-specular reflection. The number of cycles is intrinsic to the transducer and is fixed. while the frequency is some variation depending on the probe. By default, the manufacturer tries to minimize the spatial pulse length in order to maximize resolution. A high-frequency transducer allows more cycles per unit of time, allowing the spatial pulse length to be shorter. The amplitude, as in the amount of energy imparted to the ultrasound, depends on the total power, which can be modified. So why do we send pulses and not a signal continuously? That's because position is based on travel time from and back to the transducer. There is no triangulation performed to determine a position. Essentially, we have already determined that velocity within a tissue is fixed. As such, if it takes longer for the signal to travel from the transducer, hit the structure, and come back, it is deeper. Knowing that velocity is fixed, we can thus calculate depth based on travel time. This entails that you need to stop pulsing and listen for the specific pulse you sent to come back. Transducers thus alternate between sending a pulse and listening. The listening time is significantly longer than the pulsing time. A good example of how this functions is reverberation artifacts in long ultrasound. A-lines are artifacts. They do not really exist, and are rather an attenuated copy of the plural line. This happens because one pulse bounces back to the transducer, is not fully absorbed, and bounces back and forth between the two. Notice how each artifact is at equidistance from the probe. This reflects the doubled, tripled, and so on travel time. In summary, remember that distance traveled is double the depth, so double the time, and that comes into play if you're looking into more details for your exams. And I think from this you can realize that 2D imaging is actually a pulsed wave Doppler. We'll talk about transducer function, as it has a major impact on image generation, mainly because of the different ways ultrasounds are produced. We'll not go into impressive detail, but rather focus on the differences between the transducers. Linear array and curvilinear array are specific methods of generating ultrasound beams. They function by having a sequential opening of a small gate to allow pulses to come out. The same gate stays open during listening. This, in essence, limits the amount of noise coming from structures outside the beam. Once a beam is done, the next gate opens, and etc. Linear and curvilinear probes are essentially the same, with different arrangements of crystals. The linear probe has higher frequency, resulting in poor depth, great image quality, and excellent temporal resolution. The curvilinear probe has lower frequency, resulting in great depth, limited image quality, and poor frame per second. The cardiac probe is a phased array probe. It functions by opening the entire set of piezoelectric crystals and focusing them into a narrow beam. This beam is then steered through the field of view, taking into account the time delay between each pulsating element. This has some unique properties that lead to the phased array probe being an intermediate frequency, but maintaining great depth, fairly good image quality, and excellent frame per second. Linear and curvilinear probes can also be steered through other mechanisms, which allows applications such as vascular Doppler. The phased array probe also has a small footprint because all the scan lines originate from the center of the probe. The focusing allows good longitudinal and temporal resolution without sacrificing depth, as happens with linear probe. Spatial resolution is the next step and relates to the accuracy of distinguishing elements within a tissue. There are two components, axial and lateral resolution. Axial resolution is the ability to distinguish 2 points parallel to the axis of the ultrasound beam. Lateral resolution is the ability to distinguish 2 points perpendicular to the axis of the beam. Axial resolution is the simplest of the two. Essentially, it is identical throughout your beam, and actually throughout your whole image. The number of cycles in a pulse is usually minimized by the manufacturer, fixed and thus intrinsic to the transducer. Pulse length thus depends more on the frequency of the transducer, which means that high frequency leads to small wavelength. Smaller wavelengths can interact with smaller tissues in an organized fashion, and thus discern them better. Hence, as seen on the graph, a short pulse and high frequency leads to improved axial resolution. A long pulse leads to poor axial resolution, and two separate objects may thus appear as one. Notice from this graph, this is in no way related to the depth of the structures or the focal point. Axial resolution is entirely dependent on frequency and transducer. Lateral resolution leads us to introduce the concept that ultrasound beams have width, because they are the sum of multiple piezoelectric crystals being used. These beams can be focused, particularly with phased array probes, leading to a focal point. The focus point or focal point is the point of minimal beam width. Lateral resolution depends on two major principles: beam width and sequential sweep. Simply put, if two structures are closer than the width of the beam, they will be resolved as one structure. Since the beam changes width depending on depth, the focal point has the best lateral resolution. If you're sweeping across with small increments as compared to large increments, you also tend to have better lateral resolution, as you are more likely to catch each structure in a separate beam. As we said, the pulse beam can be narrowed and focused to improve lateral resolution. This focal point can be adjusted to some extent in specific machines, transducer, and profiles. Its location depends on the frequency of the transducer. A high-frequency transducer tends to have a natural focal point at equidistance between the transducer and the depth. A low-frequency transducer has a natural focal point closer to the transducer. The lateral resolution is best and increased up to the focal point or region. Past it, there is significant divergence of the beam and lateral resolution decreases rapidly. There's always a trade-off to be made between resolution at depth and in the near field. Additionally, interferences in the near field and cardiac applications limit resolution in the very near field. Finally, remember that beams are not just wide, they also have an elevation. We're not going to go into what this means in this instance because it becomes a little bit more complicated and not as useful outside of artifact generation applications. A key message practically is that axial resolution is usually better than lateral resolution and is preserved across images. It is thus mandatory to measure structures with the beam as perpendicular to the structure as possible, as in LV cavity measurements. We'll finish image resolution with the temporal resolution. Temporal resolution is essentially the ability to display images in movement. It relates strongly to the concept of frame per second generated by ultrasound machines and displayed on the screen. One of the key elements that governs temporal resolution is the pulse repetition frequency. As you've heard, the transducer has to send a pulse of wavelength and then listen for a returning signal. The listening part is significantly longer than the pulse. The number of pulses per second is the pulse repetition frequency and depends on the listening duration, since the pulse length is fixed for each transducer. So what influences listening duration? The depth of the tissue you are trying to image. The deeper the tissue, the longer you have to listen for the signal to return. As such, a shallow image has a much higher pulse repetition frequency. This will be even more relevant when discussing Doppler and aliasing. For next question, I'd just like to acknowledge Professor Stoylan for the excellent gifts that helped demonstrate these concepts. You have to understand that the concepts explained up to now are related to a single beam. The reality is that a 2D image is a sequential acquisition of small sectors of beams. To limit artifact generation, we cannot be pulsating every zone of a 2D field at the same time. This means that each sector has to be pulsed and listened for before the next sector is interrogated. This process repeats until the full 2D area has been interrogated. This is a single frame. A 60 frame per second image has this process performed 60 times within 1 second. Understanding this helps optimize our image. Decreasing the depth means that we have to listen for shorter amounts and thus interrogate the next sector faster. Without changing the width of the 2D area, we can thus increase the frame per seconds displayed. You probably have understood then that decreasing width of the 2D area means that we can return to the first sector much faster. This leads to a much higher frame per second. Both have a significant impact on frame per second. The difference between the two becomes more impactful when talking about color Doppler. Finally, we can also decide to enlarge each of the sectors with a fixed 2D area we wish to interrogate. This means that there are less events of pulsing and listening for a fixed 2D area. Logically, we can thus return to the first sector faster and generate a frame. This comes with the obvious major decrease in lateral resolution. It does not, however, affect axial resolution. To finish up, a quick word on some additional settings that will come into play in other situations. The first one is tissue prioritization. This is essentially a velocity filter that allows to select which ultrasound waves will be analyzed and displayed. It represents one of the major factors that allows us to selectively display non-moving tissues and moving elements such as blood. This will be covered in more details in the Doppler video. In summary, what's adjustable by the sonographer is frequency, power, and pulse repetition frequency through depth. What is not adjustable is your pulse duration, your wavelength, although it relates to frequency, your propagation speed, and your spatial pulse length. This is the end of this video related to physics of image acquisition. Feel free to contact us through our Twitter accounts with any questions or comments, or reach out to us at sonouni.com or YouTube channel Sonovault.